So yeah, I'm going to be talking about binary mergers, so black hole binaries, such as the one shown here, which is not an actual binary, but a visualization of a numerical simulation of a merger, as well as black hole neutron star and neutron star binaries. And so the general idea is that we are going to switch between astrophysics and computational methods during those 4 lectures. Today, I'll talk about gravitational wave sources. I'll talk about gravitational wave detections and also what we can learn from these observations. And then tomorrow morning, I'll be talking about what is needed if you want to start from Einstein's equations of general relativity and then put them on a computer and try to do simulations of these merging compact objects to generate, for example, gravitational wave models that are used by LIGO. And then Friday afternoon and Monday, we'll add matter to these systems and see what happens in black hole neutron star and neutron star mergers. First looking at all the extra physics that comes into play in those systems, and then at what we have to do to actually implement that physics in simulations. So that's the general idea. And please feel free to stop me at any time with questions. And if I don't get to lecture 4, it's not a problem because I haven't written it yet. So we'll start with an introduction to gravitational wave sources and gravitational wave production. I'm going to give you 2 views of that. First, a relatively simple, more geometric, intuitive view of gravitational wave production. And then we will look at a schematic demonstration of the lowest order production of gravitational waves, the quadrupole formula. So in general relativity, as you probably know, the general relativity is our best theory at the moment for how gravity works. And as opposed to Newtonian theory, in which we expect that we say that gravity is forces acting on objects instantaneously at a distance. In general relativity, we see gravity as space-time curvature, meaning that if you have a compact object, let's say a neutron star here at the center of the image, it is going to curve space-time around it, and free-falling objects are going to follow the shortest path through that curved space-time, which means that their trajectories get bent as they follow the curvature of space-time around, in this case, the neutron star, let's say. So if you have a rapidly moving object, it's going to be bent a little bit, like the trajectory at the top here. And if you have a more slowly moving object, it's going to be bent more, like in Newtonian theory. General relativity and Newtonian theory are pretty close to each other when you have objects which have relatively low compactness, which do not have very strong gravitational field, like in the solar system. You can measure the effect of general relativity in the solar system, but it's always a very small effect, very small corrections to Newtonian physics. If you really want to get into a regime where you can test Einstein's theory in a regime in which it is completely different from Newton's theory, what you need is very compact objects, like black holes and neutron stars, which are sources of very strong curvature. And even better, if you have very compact objects that are colliding with each other, because Einstein's theory is nonlinear, and that is the regime in which you have two very compact objects creating strong curvature that are interacting with each other very closely is the one where really we cannot predict easily what is going to happen, and the one where there's the most potential for strange things happening as well. And that's where there was the most chance of Einstein's theory breaking down overall, is when you had all those nonlinear interactions between very compact objects like black holes and neutron stars. And that's one of the main motivations to study these merging black holes and merging neutron stars. So the generation of gravitational waves now, if you have 2 strong sources of curvatures, like black holes in this case, orbiting each other, as that curvature moves through space-time, that source of curvature moves through space-time, it's going to create waves in the surrounding space-time. In the same way that if I move my finger through water, I generate waves that propagate away. If a black hole moves through space-time, it generates waves that propagate away from the binary. And those waves carry information about the motion of the object, and they also carry energy and angular momentum away from the binary. That means that as your binary loses energy, it's going to slowly spiral in. The objects are going to get closer together. as this parallel, they start moving faster and faster. If they move faster, they emit more gravitational waves. That means that the inspired is becoming more rapid, up to the point at which the two objects merge in a last burst of gravitational waves, which is what we are going to see now. So a large fraction of the energy in the gravitational wave is actually emitted in those last few orbits here, just before the merger. So that's the geometrical picture of what is happening. If we want to make predictions that are a little bit more accurate for what the amplitude of the gravitational wave signal should be, we should take a few steps back and look at the math behind Einstein's equations. And the first thing that I want to mention is that I'm going to start from the metric of space-time. If you have not seen that before, it's effectively what tells us how to measure distances in that curved space-time. The distance element, ds, the line element, the infinitesimal line element, is given by the action of the metric on an infinitesimal displacement dx. The other thing that I should point out on that slide is that here and in most of the talk, I will use Einstein notation for summation, meaning that if there is a repeated index, like the mu's and u's here, it implicitly means that there is a sum over the index, like in the middle formula here. So sum over mu from 0 to 3, if I'm in 4 dimension, and nu from 0 to 3, again in 4 dimension. And this line element is what we are, the integral of that line element over the path of an object is what we are actually minimizing or extremizing when we say that free-falling objects follow the shortest path through curved space-time. It's actually taking the extremum of that integral. So it's in that sense that the objects are following the shortest path. Now, one thing that is important to note about general relativity is that there is a lot of freedom in how you define that metric, even for identical spacetimes. Meaning I can do any change of coordinate I want in general relativity, and the metric will have a very different form by I, but it will still represent the exact same physics. That can make things very complicated in general relativity, because if you see an effect, a difference in the metric, it can be very difficult to determine whether that's because you are in a weird coordinate system, or whether it is because there is actual physics happening. I'm trying to show you that in these 3 examples here for different line elements, different metrics. The first 2 both represent standard, flat, 4-dimensional spacetime, the one that you use in special relativity. The top one is in Cartesian coordinates, and the second one is in spherical polar coordinates. The metric look very different, but it is the exact same spacetime with the exact same properties. And all physical effects will be exactly the same. It's just a coordinate transformation. Now, for this one, because we are somewhat used to working in spherical polar coordinates, we can fairly easily guess that's what's happening. But if I had a weird coordinate transformation of arbitrary form, the metric might look like something that I don't recognize at all, and it would still be flat spacetime. So that can be an issue. The last one is actually really curved spacetime. That's at each time you have a 3-dimensional sphere. So not only is it a curved spacetime, it also has a different topology from the flat spacetime above. Okay. And as an aside, you might find in different books different conventions for the signs that I'm using here. So here I'm using the convention that a negative ds square is what we call a time-like path, which is a path that is acceptable for a massive particle like ourselves moving through spacetime, meaning moving at less than the speed of light. ds square equals 0 is something moving at exactly the speed of light. It's what is called a null path. And in this case, ds square greater than 0 is what we call a space-like path, meaning that if you wanted to go from one point to the other along that path, you would have to travel faster than the speed of light, so that's forbidden. Those points are causally disconnected. They cannot talk to each other. Okay. But you might find the opposite convention, and then all the signs in these expressions are flipped. It's unfortunate that we haven't managed to agree on one, but that's how it is. So if you want to figure out what the gravitational wave emission is to lowest order, in deviations from Newtonian theory. So the simplest thing to do is probably to start from an expansion of the metric around flat spacetime. That eta is the flat spacetime metric that I just showed you on the previous slide. And if you do that, so you have your metric is flat spacetime plus some perturbation, which is your gravitational wave, effectively, right? And you have to make a coordinate choice, which doesn't really matter much, but I'm putting that here for completeness, which is a constraint on that perturbation. Now, if you do start from Einstein's equation of general relativity and just plug in that metric perturbation, what happens is that metric perturbation actually follow a very nice wave equation. So if you haven't seen that symbol before, the block symbol here is the wave operator in 3 dimensions, minus delta t square plus Laplacian. And so this is a wave equation for each of the components of that metric perturbation, with a source term which is given by the stress tensor of matter, which in Newtonian theory you can see that the 0, 0 component, the time component, is just the energy density, roughly speaking. The time components are momentum density. And this is the pressure, I guess, all the stresses, the pressure tensor, all the stresses. So this is actually a very convenient form for us to obtain because we actually know to solve the wave equation for any source term. We know that from electromagnetism, and it can be immediately obtained in integral form as an integral over those source terms. And you see that the metric perturbation at a given time and point depends on the source terms, not at the same time, but at a retarded time, because it takes a certain amount of time for information to travel at the speed of light from the source to the observer. But otherwise, you can, because the equations take this relatively simple form, once you use this linearized theory, you can explicitly write the form of the metric perturbation as a function of the source term. All right. And then, by going back and forth by going into Fourier space and back, you can actually transform this into the metric perturbation being the second time derivative of the mass quadrupole, Iij. So Iij being defined on the last line here is, as you see, the integral of T00, which is the energy density, weighted by the second order by Yi and Yj. So it's the second moment of the energy density, which is the quadrupole moment. Okay? So this tells us that the metric perturbation, the gravitational wave, is proportional to the second time derivative of the mass quadrupole. It also tells us that actually it decreases like 1 over r only with distance for the amplitude of the metric. So that's what we can get from this formula. We can also get an idea of what the amplitude of gravitational wave is, which is what we would like to detect. And to do that, we can replace the quadrupole moment roughly by, for a binary system, quadrupole moment is going to be proportional to the mass of the system times the binary separation square. And if I want the second derivative of that quadrupole moment, it's going to be the mass times the mass separation square times the angular velocity square, order of magnitude, which is just mv square, with v being the velocity of the objects in the orbit. So if I do that replacement, I end up with the order of magnitude expression, which is shown on the right here, Gm over RC square, which is Gm over C square is the gravitational radius of the black hole. So that's the size of the black hole divided by the separation, by the distance to the observer. So that's a very small number. It's the size of a black hole divided by the distance between us and the black hole. The black hole is maybe 10 to 100 kilometers, depending on the mass of the black hole. And we are a billion light years away. So that's the main reason the amplitude of gravitational waves is so small. That's the ratio that you're expecting. That's the amplitude that you're expecting for gravitational waves. It's extremely small. And then there is a factor of v over the speed of light square. And that for most objects is small, but for merging black holes is actually of order 1, because as they get close to merger, they're moving at roughly the speed of light. So that gives us an idea of what kind of signal we should be looking for when we are looking at gravitational waves, that it's going to be an amplitude which is extremely small, which is comparable to the size of a black hole divided by the distance to the observer. The other question that we should ask ourselves if we want to actually observe this is what does gravitational waves passing through the Earth look like to us, to an observer? And to do that, we have to look at what it looks like as a 4x4 matrix, what the metric perturbation looks like. And for a convenient choice of coordinate, which I'll come back to, you effectively have two free components of the metric. And I'm first going to show you what they look like, and then we can more carefully look at what it means. You have an H plus component here, which only comes in the HXX and HYY component of the metric perturbation, in this case, assuming a gravitational wave is moving along the z-axis. That means that when distance measured in the x direction increases, distance measured in the y direction decreases. And then it oscillates back the other way, and they keep oscillating out of phase with each other. So that's the one that's shown on the left. The one on the right is the cross-polarization of gravitational waves. It's the second possible polarization. That tells us that if I am in the plus x plus y direction at 45 degrees from the axis, and the distances are being measured as increasing, then at 90 degrees in the plus x minus y direction, distances are decreasing out of phase, and then they keep oscillating that way. At 45 degree rotation from the H plus polarization. Okay? So those are the two possible polarizations. Now, we know this now, and you will find that in many descriptions of gravitational waves. It was not always obvious. I skipped a step here because there is a fair amount of math, which is the choice of coordinates that gives you this convenient expression for the metric perturbation. But there were other components initially. Let's go back to expression. At this level, for example, HZZ was not 0. There was no specific reason for HZZ to be 0. But as it happens, if you make a coordinate change, you can remove that component from the metric. Now, the question that for a certain amount of time after general relativity was proposed was, well, do even those remaining components have anything real to them? Or are they just a change of coordinates? And this is not a simple question to answer. For a long time, Einstein himself said that gravitational waves were just a coordinate effect, that there was nothing real about them. It took a long time to figure out whether it was real or not. And maybe the best argument eventually to show that they are is that they actually carry energy away from the system. They decrease the energy of the binary. And that would not happen if it was just a coordinate effect. But it is not obvious just from the equations, because it's easy to prove that there exists one coordinate transformation that zeroes all those other components, because you just have to show one. But it's hard to prove that there is not one coordinate transformation about all of the infinity of coordinate transformations that are possible that doesn't remove those other components here, the h plus and h cross. All right, so now we have an idea of what the amplitude of a gravitational wave is. We can actually look at what it would look like for black hole, neutron star, neutron star binaries. And I'm going to show you a few plots like this over the course of the 4 lectures here, so it's good to spend a little bit of time looking at what it means. This is, on the horizontal axis, the frequency of gravitational waves. And on the vertical axis, you see the amplitude of the signal in Fourier space, in frequency space. Right? So it's the amplitude of the Fourier transform of the gravitational wave signal. And the red curve is what we call the LIGO noise spectrum. Effectively tells you when LIGO becomes sensitive to gravitational waves at a certain frequency. And we will see a little bit later what actually sets the limits of that curve. But for the moment, let's just assume that it is correct. And we see that LIGO is particularly sensitive around about 100 Hertz or so. That's where gravitational waves are good for LIGO to observe. So what does that correspond to? Well, if you use the quadrupole formula, we find that the frequency of the gravitational waves is twice the frequency of the binary orbit, because that's the frequency at which the quadrupole varies. And you will see that it scales linearly with the mass of the object. So more massive objects have a larger gravitational wave amplitude. More massive objects are also orbiting each other at a lower frequency when they get close to merger. So typically, more massive objects are shifted to the left of this plot, and less massive objects get shifted down because the amplitude decreases, and to higher frequency for the same phase in the, yes?
I'm just curious, the noise curve has little peak at 500 Hertz, why so?
So the actual noise curve has a lot of little peaks everywhere. For any resonance in the big LIGO detector will create a peak. There is a huge one at either 50 or 60 Hertz, whatever the American use for the. There are some that are resonances in the pendulum that is used to suspend the masses. There is one, which maybe I should do one shown here, which is put on purpose to calibrate the detector. I honestly don't know which one this one is. I don't remember. but the actual noise spectrum, and I don't know if I have it here, but I can show it to you later, has a million of those lines all over the place. This is an idealized version of the LIGO noise spectrum. Actually, maybe a little bit later. No, this is also idealized. I don't have the full one here, but I'll try to show it in the lecture later then. The one that they actually observed during observations. But yes, this is a very idealized version of what the noise curve is. That's what they are aiming to, but it's never going to happen exactly like that. Okay, so what LIGO is the most sensitive to, if you actually look at what the frequency of a given black hole binary is when it is in closed orbit, so a few gravitational radii away from each other, the black hole and the black hole are in a frequency which is nearly the same frequency as for Keplerian orbits. You find that a 30 solar mass plus 30 solar mass black hole is going to merge at about 200 Hertz or so, while a 10 solar mass is about 3 times higher, and neutron stars, which are about 1 to 2 solar mass, are going to be merging at much higher frequency. So what does this mean for what we are actually observing with LIGO? Well, the evolution of a binary on this graph, a binary starts way to the left at very low frequency when the objects are very far away from each other, orbiting slowly around each other. And then it starts emitting gravitational waves, and the frequency of the orbit increases over time. So the object moves to the right here. And as the evolution accelerates, it moves faster and faster to the right, up to the point where the merger occurs, and then the gravitational wave signal shuts down as the object settles to a single black hole. You will note that as you increase frequency, the amplitude here decreases, which is the opposite as what I said earlier. And that's because at a given time, the amplitude of gravitational waves increases over time, but the system is also spending less and less time at a given frequency because it's inspiring faster and faster. So the actual power at a given frequency decreases as you increase frequency. It's a consequence of the gravitational wave emission accelerating the inspiral as time goes by. So for a very massive black hole, you see the last few orbits, maybe for a 30 solar mass black hole, 4 or 5 orbits before merger, and then the merger. If you look at the much less massive neutron stars, you catch them a lot earlier in their inspiral when they are farther away from each other relative to their size. And so you see many, many orbits, but then it goes out of the band of LIGO before they actually collide. And so you miss the very last part, which is unfortunate because it's maybe the most interesting part for neutron star mergers. But it's very hard to see that part at high frequency. So that's something to keep in mind when you look at what LIGO is going to see for any given binary, is that which part of the binary you are sensitive to depends a lot on the masses of the system. And if I had two 1,000 solar mass black holes, everything would happen to the left of the plot here, and I would not see it at all. I need Lisa for that. We'll see. That's the wrong direction. Okay. So what are the sources of gravitational waves that LIGO is actually sensitive to? Well, there is mainly black holes at the moment. LIGO has seen 5 or 6, depending on who you count, black hole binaries. Maybe more if they leave us with some surprise in the release of the full data for 402. They have seen one neutron star merger, which is the signal represented in the middle here, which we will talk a lot more about on Friday. They haven't seen a black hole neutron star merger, which is the second one here, but hopefully they should be able to reasonably soon. It depends on what the actual rate of merger of these events is, which we don't know at all because we haven't seen a single one. But it actually should be sensitive to black hole neutron star merger reasonably far around us at the moment. So, well, not at the moment because LIGO is not taking data, but whenever it comes back online. It is somewhat sensitive to core collapse supernovae. Core collapse supernovae have gravitational wave emission around a kilohertz, roughly speaking. And it's a lot weaker than for those compact object binaries. It's used to the asymmetries in the collapse of the star. And Philippe Mostar will talk a lot more about core collapse supernovae next week. But broadly speaking, we can observe the gravitational waves from a core collapse supernova if it's somewhere in our galaxy. Depending on the supernova, maybe halfway through the galaxy, maybe in nearby satellites of the Milky Way if we are lucky, but of that order, not in another galaxy, like for black hole, neutron star, black hole mergers. The object represented on the left here is interesting if we ever get to actually see it. It's a rotating neutron star. Now, a rotating neutron star, if it's perfectly axis symmetric, is not going to be a source of gravitational waves. It does not have a time-varying quadrupole. But if there is a very small mountain on the neutron star, or a big mountain, but we know there is no big mountain. If there was a very small mountain on the neutron star, it would be a source of gravitational waves. And when I say small mountain, what we generally think about is a centimeter, maybe, on the top of the neutron star, which is 10 kilometers big. Don't think about Everest or anything like that. It's a very, very small distortion in the neutron star. And that, if we have that on a very nearby neutron stars, we should, one where we know where the neutron star is because we observe it by other ways, we should actually be able to observe distortion in the size of the in that neutron star. Those very small mountains. But LIGO hasn't been able to do that yet. So we'll see what happens. The constraints on how big of a mountain you can have on a neutron star are pretty tricky to get and very uncertain at this point. This is an image, by the way, from the, yes?
How long would such a signal be?
Well, that's a very good question. That depends how long it takes, I suppose, for the mountain to form or disappears, what actually causes it. In theory, compared to the lifetime of LIGO, it might be, what LIGO is technically looking for is a continuous signal. So that's the way they look for these things. So at least on the timescale at which LIGO takes data, it's expected to not change, or that's what LIGO would see. Now, how long they would last in practice, I honestly have no idea.
So this would be an
Yeah, it will be there all the time, and so it's a very different search process from the other ones. That the other one, you have a theoretical signal for black hole binaries, and you continuously sweep your LIGO signal for something that matches that theoretical prediction. Here, for the neutron stars, the search where they can look for the signal deepest in the noise is you know where the neutron star is because you have seen it by other means. And you know what the rotation period of the neutron star is, maybe because it's a pulsar. And you also probably know what actually the rotation period time derivative is. And then you look for a signal that is at exactly that frequency, at exactly that location, for the entire duration of, ideally for the entire duration of your data taking with LIGO, but that's too computationally expensive, so what they actually do is they divide it into small chunks and try then to add that together. But that's the general idea for those search for single neutron stars. So it's actually a completely different pipeline from the main binary search, and it is also extremely computationally expensive. It's okay for those single neutron stars where you know where they are, what the frequency is, but they also have more generic searches where you only know some of those parameters. And if you wanted to do a search for all possible neutron stars with all possible frequencies, that becomes really, really expensive. Is that okay? Yep. Yeah, and so the last one here, I think they put in the press conference just to say whatever we don't know and hope to see one day, because it's nice to have a detector that observes something new like gravitational waves. It's an entirely new way for us to observe things in the universe. So hopefully at some point we will see something that we don't predict. It would be nice. This one is cosmic strings, but really it could be anything. The whole point is that we would like to be surprised. But we haven't been so far, so we'll see. All right, so let's have a look now at what is actually involved in detecting these gravitational waves. And I'm going to focus mostly on the LIGO and Virgo detectors, because those are the ones that have actually seen gravitational waves so far. But I'll also say a few words about other methods later on. So the general idea is to rely on the geometry of these metric perturbation, right? We know that if a gravitational wave passes through the Earth coming from above the detector, and you have a detector like LIGO, which is a big L, while as the gravitational wave passes by, one arm of the detector stretches, the other one, well, not stretches, but the distance of the arm looks like it's becoming higher, the other one as it becomes shorter, and it oscillates that way. And so LIGO is going to take advantage of that by measuring changes in the relative length of the two arms of the detector. And as we already said, this is a very small change of the order of 10 to the minus 18 meters or so for LIGO, which is about 4 kilometers long. So it's an extremely small change that you have to measure here. Yes, okay. So the general idea is that you have an interferometer. So you shoot a very powerful laser beam into the two arms of the detector. It splits into two. It is reflected on suspended masses at the end of the arms. And that's the distance that you're actually measuring, splitting the beam splitter and the masses. And then you recombine them. And if the two arms are exactly the same length, they add constructively. If they are half a wavelength of the laser beam apart, they interact destructively. And so you can measure changes in the length of the detector, which are a small fraction of the wavelength of the laser in theory. That wouldn't be enough. There are a lot of other things that go into LIGO to actually get it to the sensitivity of 10 to the minus 18 meter. One of them, the easiest to explain, is that there is an extra reflecting mirror in each arm of the detector, which means that your laser beam doesn't go once round trip in the arm of the detector, but actually goes hundreds of times back and forth in the detector before escaping on average. And so that makes the length of the detector, the effective length of the detector, much longer than 4 kilometers. There is also a lot more optics that go both into ejecting the laser and into extracting the signal at the end that I don't have the time to get into. Okay, so before looking at what is actually limiting the accuracy of LIGO, let's think about what LIGO can actually see and what it cannot see. So, good question. What do you think LIGO see if this waveform polarization, a plus polarization, comes from above the detector and passes through the Earth? Nothing. Yes. Nothing. Because the two arms change in phase. Their lengths change in phase. So the relative distance between the test mass, the relative change is the same for both arms of the detector. And the two laser beams are covering the exact same length. And so there is actually no interference pattern at the end of the detector. You need the two arms to change their lengths separately in order to actually see something with LIGO, right? Okay. There is actually also directions from which LIGO is sensitive to no waveform polarization. If you have gravitational waves which you imagine comes in the plane of the detector, okay, so let's say that I'm the detector and the gravitational waves come from you towards me, then whichever polarization I get is going to change both arms of the detector at the same time, and I cannot see anything. So in that direction, and from behind me as well, I'm entirely insensitive to gravitational waves. So each of the detector has some blind spots, and each of the detector, even outside of its blind spot, is only sensitive to one polarization of gravitational wave, not both. Okay, so what is actually limiting the accuracy of the LIGO detectors? And I think looking at what is limiting the accuracy of these detectors is a good way to see what a feat of engineering it was to actually construct these things, because they are really limited by quantum noise in the majority of their sensitivity band. We can see that in this plot here, which lists the main source of noise in the LIGO detector as they are expected to be a few years from now. They are not quite there yet, but they are getting fairly close. You can see that at very low frequency, it's the brown curve, which is the first thing that would generally come to mind, which is seismic noise, just the vibrations of the Earth, which will change the length of the detector. That is to be expected. But LIGO has such good suspension for its test masses at the end of each arm that they can basically remove the impact of the motion of the Earth everywhere above a design sensitivity 10 Hertz, currently more like 20, 30 Hertz. They haven't quite reached that point. And that's actually one of the main improvements between the LIGO from the 90s and the LIGO from now, is that before it was just mass suspended from a single pendulum, and now it's a 4-arm pendulum with fairly complicated dampings that is actually holding those masses together, and which is capable of damping basically all of the motion of the Earth above 10 Hertz. Then there's a very short region between 10 and 20 Hertz where you expect to be limited by dissipation of in the suspension for those pendulums, and also by the green curve, which is interesting. It's gravity gradients. What gravity gradients are, it's that as matter in the Earth moves around due to seismic motion, the gravitational potential of the Earth changes, and that actually affects the test masses. And you cannot shield against that with pendulums. It's a force at a distance in Newton theory, I suppose curvature in general relativity. And your pendulums are not going to protect you from that. It's a very small effect, but it's sufficient to be noticeable in a very small range of the LIGO band. So there is not much you can do about that one. And then everything above 30 Hertz basically is quantum noise. And by quantum noise, what we mean is the Heisenberg uncertainty principle. That is what is actually limiting the sensitivity of the detector everywhere above a few tens of Hertz. And that comes into basically two ways. At high frequency, it's the fact that you don't have many photons to sample your signal at those high frequencies. You have a limited number of photons due to the limited power of your laser. And those photons have an uncertainty in their time of arrival. That means that you have an uncertainty in the phase of the gravitational wave signal, because you don't know exactly when the photons are arriving because of quantum uncertainty. And at lower frequency, it is variation in the radiation pressure that acts on the mirror. So you have that very strong laser beam which continuously pushes on the mirrors at the end of the detector. And because the photons forming that laser beam arrive at slightly shifted times due to random quantum fluctuations, that pressure actually changes over time. And that is actually why we end up with that bucket shape for the gravitational wave detector, is that if you increase the power of the laser beam, you gain sensitivity at high frequency because you have more photons, but you lose sensitivity at low frequency because you have more photons. And if you instead lower the power in your laser beam, you can decrease the noise at low frequency, but then you increase the noise at high frequency. And so you have to make a compromise here. And of course, the compromise is made so that you are going to be as good as you can be to detect black hole and neutron star binaries. It would be very hard to go to lower frequency because then you have all those other sources of noise that come and kill you. But in theory, you could be a little more sensitive at high frequency if you are able to build optics that can resist the kind of very high power laser that you will have to put through it. And that's something that LIGO is working on. They are trying to increase the power of the lasers, especially to be more sensitive to things like neutron star mergers at high frequency. But it's a complicated thing to do because generating that kind of power within the complicated optics that LIGO is using to measure things at quantum fluctuation level is not an easy task. Yes?
How does LISA get around the gravity gradients?
LISA is very far away from the Earth.
Okay.
Yes. LISA is about a month behind the Earth on its orbit. I haven't heard much about how LISA data analysis is going to work, but so maybe they do have to make some corrections from the point particle. I'm not sure, but they might be able to treat the Earth as a point particle for.
So what's going to be on the leftmost side of the sensitivity curve to the low frequency?
For LISA, low frequency. It's a good question.
It's confusion noise from white wolf binaries.
Is that the actual? I mean, yeah, that's certainly the main component in the bucket. Yeah, in the most sensitive region, it's certainly white dwarf binaries. It might be. Yeah, I don't know if it's at low frequency also. In a sense, yes. Gravitational waves of many binaries. That's certainly the dominating factor at the most sensitive region of LISA. I'm honestly not 100% sure about the low frequency part. The high frequency part is definitely laser power, but yeah, I will have to come back to you on that. Okay, but before getting into LISA and other gravitational detectors, let me finish the ground-based interferometer detector. Currently, we have 2 detectors in the US, the LIGO detectors, one in Washington, one in Louisiana, and one in Italy, the Virgo detector, close to Pisa. Both of them, all 3 of them were constructed first in the 90s, stopped taking data to get a lot of upgrades, including those changes to the suspension that I mentioned, and big increase also to the laser power that is still coming. So they started taking data a long time ago, but they were not sensitive to anything astrophysically until basically 3 years ago now. And Virgo started taking data again with an updated detector about a year ago now. The GEO detector is a German detector which is much smaller and is used to test new technologies, whatever you want to implement in the future in your detectors. And then there will be one in Japan and one in India, which are still Japan under construction, and I'm not even sure that construction already started for the LIGO India. I think they're still working on finding a site, exactly. But those should follow the Japanese one within a few years. It's not going to be 2018, that's an old slide, and it's definitely not going to be 2018, but within a few years, and LIGO India probably a little bit after that. Now you might wonder, why we actually need that many detectors. They are pretty expensive detectors to build. So we better know why we would like why we need to have that many. Having 2 is absolutely necessary. Having 2, we wouldn't be able to do anything if there weren't at least 2 detectors running. The reason for that is that because we are doing such a sensitive measurement, if we see the signal in only 1 detector, we just don't believe it. It could be a truck on the road next door, and you would see a lot of signal in 1 detector. So you need to at least see the same signal in 2 different detectors, which are sufficiently widely separated in space that they don't receive the same local perturbations. So that's the main reason for having at least the two US ones, and that's why we needed both of them to make a first detection. Another advantage of having multiple detectors, besides confirming each other's results, can be to be sensitive to multiple polarization of gravitational waves. And we see that gives you a lot more information about the properties of the binaries. And so for that, you need detectors which are not oriented in the same way. So one like that and one like that, for example, would be giving you both polarizations. That is not what the 2 LIGO detectors are. The 2 LIGO detectors are nearly in the same orientation because they are built to confirm each other's results. So they want to be seeing the same gravitational waves. But some of the others, on the other hand, have whatever the convenient orientation on their side was. And I suspect that for LIGO India, at least, which is only being constructed now, they are going to think very carefully about how to optimize the orientation so that it helps as much as possible with polarization of gravitational waves. And the very big change with the arrival of Virgo into the whole gravitational wave detection picture is localization of the sources of gravitational waves. If I have 2 detectors, the way gravitational wave detectors can determine where in the sky a signal is coming from is basically by looking at the time of arrival of the signal. You do triangulation. So I see that the Washington detector saw a signal 2 milliseconds before the Louisiana detector. And from that, you can describe an entire circle on the sky from where gravitational waves might be coming. That's not great, an entire circle on the sky. There's a lot of things on the sky within a big circle that covers the entire sky. So if you actually want to do localization of gravitational waves, you need a 3rd detector. And then you actually can have, well, if we had a very high accuracy, a point, but it's never going to be like that, so at least a very small region that you can limit yourself to. And that's very important if you want to do electromagnetic follow-up of these gravitational wave signal. For example, in the case of neutron star mergers, where we expect electromagnetic counterparts. For black holes, people will still look, but the chances of finding something are a lot lower. All right. So LIGO is not the only detector taking data at the moment. There is actually one other type of, well, LIGO and Virgo. There is also one other type of detector which is actively looking for gravitational waves from compact binaries at the moment, and that's the pulsar timing arrays. There are multiple iterations of this, but they all use the same principle. And it's a pretty neat idea. It's to use the fact that we have a lot of pulsars around us in the galaxy, and for at least a few of them, we have a very good measurement on exactly when each pulse should arrive, to better than a microsecond in some cases. And if we know exactly when the pulse should arrive, and the gravitational wave passes through the galaxy, now the distance between us and the pulsar is going to change. If the distance between us and the pulsar changes, then the pulse is going to be a little bit delayed or a little bit earlier. And if the change is sufficient to be larger than the accuracy with which we know the behavior of the pulsar, then we can actually have a measurement. Again, one pulsar is not going to be enough to convince us that we have seen gravitational waves, because there could be a lot of astrophysics going wrong between us and the pulsar. On the other hand, if you see 20 pulsars and they have a change which is correlated in the manner that you would expect for gravitational waves passing through the galaxy, then you have a pretty good idea that what you are seeing is a gravitational wave passing through the galaxy. So you use, well, actually, those timing arrays tend to be mostly dominated by what they see from the best 3 or 4 pulsars at the moment. Using that, you can try to see whether a gravitational wave is passing by. This is a completely different regime from LIGO. Obviously, we don't take data from every single pulsar every millisecond, so you're not going to be sensitive to kilohertz gravitational waves. You're sensitive to very slow variation in the gravitational waves. Typically, that means that you are going to be sensitive to very, very massive black hole, 10 to the 8 to 10 to the 10 solar mass black hole in those PTAs. They haven't seen any gravitational waves yet. They also most likely won't be sensitive to a single loud black hole, but rather to the combination of multiple merging black holes in multiple galaxies, adding their contribution to the gravitational wave signal. And that might take a few more years for them to get there. We don't exactly know. But they're already starting to put interesting constraints on the rate of merger of those supermassive black holes, which is interesting for if you want to, for example, to compare to the prediction of cosmological simulations for how often supermassive black holes merge at the center of galaxies. So it's already starting to do some very interesting science. Unfortunately, it's not an actual detection, which is always more exciting.
Would it be neutron stars? Not black holes? That's our time difference, right?
So sorry. Okay. So you detect gravitational waves coming from pairs of merging black holes. You detect them because you see the distance between us and a neutron star changing. Okay. So let me. Right, so let's say I have a binary black hole here, very far away. Moving on. And then I have the galaxy over here. It's us here, and then a neutron star here, a neutron star here, a neutron star here, a neutron star here. And the gravitational wave is passing by, and maybe this pulsar is moving away. This one is moving away. This one is moving slightly in this direction. It's not actually moving. Okay, it's the distance measurement changing because gravitational waves are passing by. But for convenience, maybe draw arrows. And this one appears like it's moving also maybe towards us, or maybe not at all actually in this direction, because it's at about 45 degrees. And so if we see this pulse coming late, this pulse coming late, this pulse coming early, we know that there was maybe a merger all the way over there. It's using the neutron stars are the detector, the black holes are the source. That's a very good question. Okay. So we already looked at LISA. So LISA is closer in principle to what LIGO does, except that it's bigger and it's lasers in space, so that's cool. You have 3 satellites that are going to be launched about a month before the Earth on its orbit, on the same orbit around the Sun. And they are separated by a few million kilometers. And of course, because we are putting those lasers on satellites, they're not going to be as powerful as the lasers that you can build with LIGO. But still, you can actually measure gravitational waves roughly in the range of 10 to the 3 to 10 to the 6 solar mass for black hole mergers. But as we already mentioned, this is not actually what LISA sees the most. LISA is mostly sensitive to white dwarf binaries. And that's what is going to dominate the signal. And actually, the data analysis process for LISA is very different than from LIGO, even though the detectors look very much the same. Because data analysis in LIGO is trying to find one signal in a lot of detected noise. Data analysis in LISA is trying to understand the signal from hundreds of sources at the same time in one detector. That's a very different problem. And that's a problem that has not been entirely solved so far. There is still, about 16 years to figure it out before LISA launch. But it's something that has become a bit of an urgent problem in astrophysics, is actually trying to figure out how to do the data analysis for LISA when it's going to have all of those combined systems together. That's going to be one of the big challenges coming with that gravitational wave detector. Right, and so if we had all of that, then we would have actually multi-frequency gravitational wave astronomy in the same way that we have multi-frequency electromagnetic observations with the pulsar timing array in the nanohertz regime, LISA in the millihertz regime, and LIGO at about a kilohertz. Right. So LIGO being sensitive to then solar mass objects, LISA thousands of solar mass for the mergers or white dwarf binaries long before they merge. and pulsar timing array for billions of solar mass black holes merging. Any question on the detectors before I switch to a different topic? Yeah.
There's a question. Now we've been thinking about the detections of only the gravitational waves with LISA, with LIGO and Virgo and so on. And the question is, can we trace by the signal of the gravitational wave the particular source of the gravitational waves, the black holes, neutron stars, and to say the particular coordinates and spacing?
Right. Yeah. So that's where having multiple detectors really help you. So for LIGO and Virgo together, you can get a reasonable idea if all three detectors are taking data at the same time. And I'll show you a plot later on. You can have a reasonable idea of what it is within maybe 10 square degree or so. It's not great by astronomical standards, but it's much better than with two detectors, where it's hundreds or 1,000 square degrees. And then people don't even try to search that. Well, they try, but it's pretty hopeless. So yeah, with three detectors, you can do it. LISA won't be great for that. Because you have only one. I mean, you have three arms, but you have only one detector, so it's not going to be. And with the pulsar timing array, you have some directional information. You have different directional information because you have many pulsars in different directions, which you can use to get directional information. But it's probably going to be sources that so far away that I doubt that we would actually be able to see them in by other means, unless we are really lucky. I think we wouldn't be able to see them in electromagnetic observations.
So for all the gravitational waves we have now for all these detections, we do not know the sources, or we do know.
So
Or we can only just
this is a sky localization for the gravitational waves that we have so far. You see that all of those that are GW15, which are the ones from 2015, are very bad. The reason we say it's black holes is because they are very massive. That's it. We haven't seen anything, and we cannot really put constraints on whether there was an electromagnetic counterpart or not significantly. I mean, if there had been a bright gamma ray burst, we would have seen it probably. But besides that, in the GW17, you see that the first one is the purple one at the top. That's still without Virgo. And then 1708-14 and 1708-17 is in the few weeks where Virgo and LIGO were all taking data together nicely. We had two sources coming in that small time period. LIGO has been very lucky multiple times. And there you see the very big improvement, right, in the localization. And then that's all for 1708-14, but for 1708-17, then we have all of the electromagnetic observations that follow that actually show us exactly where it is, the host galaxy, and even the localization with respect to the host galaxy that we know for that specific object, but not from gravitational waves, from the electromagnetic follow-up. Does that answer your question? Yeah.
About this pulsar wave detector, does it already exist, or it will be launched sometime?
Which one?
Pulsar-based.
Oh, the pulsar. So that already exists. The pulsar timing array. There are multiple collaborations that are taking data. They are continuously trying to add new pulsars to make the detector more sensitive, or to increase the characterization of the noise of the pulsars to make the detector more sensitive. But actually, what really improves the quality of pulsar timing array is just waiting time. The more time you wait, the better your noise flow becomes. But they are taking data. They have been taking data for multiple years now. They are a little bit at risk because funding for the radio observatories that they are using is not guaranteed, far from it. And if we lose the main radio observatories that are used to characterize those pulsars, then suddenly it becomes very hard to do pulsar timing. But they're already taking data, and they already have constraints on gravitational wave emission. It's just they haven't seen any. That's all. But they are taking data, yes. All right. So finish this lecture, I'm going to have a look at what we can actually learn from gravitational wave observations, and what are the main parameters that we are sensitive to when we do. Why is LIGO more sensitive to some parameters of the binaries than to others? You might have seen some parameter estimation from LIGO, and it can look weird what LIGO is sensitive to and what it is not. So let's look at what actually determines what the main parameter observable by LIGO is. To do that, actually, we can go back to our estimates of at lowest order deviation from Newtonian theory of what the gravitational wave signal is. And I'm going to start from the energy in the gravitational wave signal, which is the equivalent of the Poynting flux, if you want, for gravitational waves. That's proportional to the third time derivative of the quadrupole moment. So it's the square of the time derivative of the gravitational wave amplitude. Now, I'm going to consider the binary, but I'm no longer going to assume that the two masses are the same, because part of what I want to show you is why it is a weird combination of the masses that LIGO is sensitive to. So no, they are no longer the same masses. So if I actually compute time derivative of that, the time derivative of the mass quadrupole, well, it is the mass quadrupole is times something which is proportional to either cos or sine of 2 omega t, depending on which component of the stress tensor you're looking at. Let's say cos for here. Doesn't really matter at this point. So the third derivative, the third time derivative of this. So you are going to have something which is proportional to the frequency of the system to the third power times the quadrupole of the binary. Now, I actually know from Newtonian theory, and here I'm only doing deviation from Newtonian theory, so I'm assuming Newton is correct for everything but gravitational waves. I know from Newtonian theory that the ratio of the distance from object 1 to the center of mass divided by the separation between the two objects, which I'll call d here, is the ratio of mass 2 to the total mass of the system. And so I can replace R1 and similarly R2 in this formula and have that shown to omega cube. So that's just replacing with Newtonian orbital positions. This is cube m1, m2, d square. There's a d square here. Okay. So that tells me that from that I can derive what the energy in gravitational wave is. Six m1 m2 square d4. Yes. The other thing that I need is, so this is the energy lost by the binary. The energy of the binary at a given separation now, is half the potential energy. The potential energy plus the kinetic energy of the two objects. And so the time derivative of this should be equal to minus the gravitational wave energy loss. And to actually get there, I need to also use the relationship between frequency and separation, which again I'm going to use just Kepler's law. I'm doing only Newtonian theory here, except for gravitational waves. So I can replace the distances everywhere, the separations everywhere by the frequency. Gives me sorry, this is the total mass here. Yes, it's the total mass. All right, so now I can actually take the derivative of this. The only thing that changes over time, assuming that the masses are constant, is the orbital frequency. So that being the G somewhere actually, but it doesn't really matter here. Right. Now this one should be equal to, this is proportional again. I have left some numerical factors out. This one and this one should be exactly opposite. If I want the energy loss from gravitational waves to correspond to the energy that the loss of the binary as it's parallel. And so if I equate those, I'm going to end up with a dot equal third so right. So if I equate the loss of energy of the binary to the energy that the binary is emitting in gravitational waves, I end up with a relationship that only involves the change in frequency of the orbital motion, the actual frequency at the current time, and the masses of the two objects in that weird combination here of m1, m2 over m1 plus m2 to the 1/3, which is the Chirp, which is the Chirp mass to the 5/3. So the Chirp mass is defined so that whatever in that combination as the unit of mass comes out. So yeah, so go back there. The Chirp mass is defined here so that it's something that has the units of masses and as a proper combination of m1, m2, and m1 plus m2. Again, I should have written proportional instead of equal. Otherwise, it's nothing. Correct. So,
Is there physical interpretation for the chirp mass?
sorry?
It's just a special combination.
Sorry?
Is there physical interpretation for the chirp mass?
To me, it's the rate at which it's losing energy, if you want. I haven't heard a good explanation for physical. I think it's more it's the one parameter that comes in when you actually compute to lowest order that you can possibly compute what the emission of gravitational wave is. Because if you have that and you assume that this is not an approximation but it's the exact solution, then you can compute the evolution of the system and the gravitational wave signal at all times. If I know what the initial separation and thus the initial frequency is, from this equation, and I know what the masses of the objects are, let's assume, from this equation I can compute the frequency of the gravitational wave at all time. It's just a first order differential equation for omega. And if I know the frequency of the gravitational wave at all time, I can actually get the waveform. I know what the amplitude of the gravitational wave is as well from the quadrupole formula. So from this formula and the quadrupole formula, I can get the entire gravitational wave signal to lowest order around Newtonian theory, right? And so that's why this weird combination of the mass, the chirp mass, comes out as the main parameter in the LIGO data. It's a combination of the masses that you end up with if you actually equate the energy lost to gravitational waves to the change of energy of the binary. And to lowest order, that's the only thing you're sensitive to. As I mentioned, that's the only parameter that comes in if you want to compute the gravitational wave signal to lowest order. So for a low amplitude signal, for a signal that doesn't have much signal to noise, this is basically the only thing that you can measure. Anything else that you would try to measure is a perturbation on this derivation. Nearly everything, except the merger. The merger, this of course holds only during the inspiral. Okay, so for example, here is the neutron star detection by LIGO. Thank you. Yes. Otherwise, we'll never see the tracks. So each of those plots on the right gives you the spectrogram of the gravitational wave signal as observed by LIGO and Virgo. You can only really see the track of the spectrogram in one of the LIGO detectors, the Livingston one. You can see pretty clearly the evolution of the frequency over time. In the Hanford one, you can see the end of it. This signal happened to be in a blind spot of Virgo. So if you see something in Virgo, I would be interested to hear about it, because normally there isn't supposed to be anything. But the Livingston one has a pretty nice track starting pretty early, giving you the frequency evolution. And from that, you can find the chirp mass with extremely high accuracy. And that gives you, when you actually compute what the masses of the individual objects were, with that weirdly shaped banana here in the mass 1 versus mass 2 plot. This is a curve of constant chirp mass in that space. Okay? If the chirp mass was a little bit higher, that curve will be shifted up. If it was a little bit lower, it will be shifted down. And if the chirp mass was a little bit higher, that track of the neutron star merger would look very different. It would evolve a lot faster. If the chirp mass was a bit lower, it would evolve a lot slower. So you would immediately see the difference. The one thing that you could get one of the spectrogram and look by eye, get an estimate of the chirp mass, or just draw a curve that is the integration of this formula, and you could get you could get the chirp mass immediately without doing any sort of fancy parameter estimation with LIGO. It's for all of the other parameters that you need to get fancy. To get the chirp mass, you could just look at the track and get it immediately. Any question on that? Yep.
What is the product of the neutron star merger?
Sorry?
What is the product of the neutron star merger? Is it a whole?
That depends on the neutron star merger. Do you mean this one specifically? This one specifically, or in general?
In general.
In general, it can be a black hole, or it can be a neutron star that rapidly collapses to a black hole, or it can be a neutron star that remains a neutron star for as long as you can see it. It can be any of these. And I'm going to talk a bit more about that probably on Friday afternoon. I think Sylvia already showed some different outcomes in her talk. I don't remember if you had one that collapses or not, but yes, of course, yes, with different masses, yes. Yeah. So in Sylvia's talk, there was the different total masses of the neutron stars. If you have high mass systems, it collapses to a black hole, and if you have a low mass systems, it remains a neutron star. And we can make that a little bit more accurate. We'll talk about it later. But that's the general idea. That's what numerical simulations from many different groups have shown over the years. It's a good place to finish. We just show the. No, it's good.
2 minutes, no problem.
No, we just finished the chirp mass. I'm going to talk about the other parameters that we can derive and the LIGO results, but that's actually good to do at the beginning of next lecture. So let's do that.
Okay, thank you.